All right, today we're going to take a look at something called Taylor polynomials. In particular, we're also going to look at another type of polynomials called Maclaurin polynomials, right? So let's do a little bit of writing together about why we're making this shift. All right, it didn't work. All right, I'll use my hand. All right, a compelling reason for considering series is that they are an essential means for exploring and computing transcendental functions. I hear whispering going on. Do you guys know what transcendental functions, what that means?
We're talking about transcendentalism.
Oh, you were going to use it in a different way. Okay. All right, just out of curiosity, who took Calc 2 here? Okay, everybody but David. Who took Calc 1 here? Everybody but David. With me, I know, yeah. Okay. Okay, so do you remember, everybody but David, do you remember in Calc 2, there was a point at which you learned some new derivative and antiderivative rules that you didn't learn in Calc 1? Okay. Those rules that you learned, and I'll write down for you just a moment here what some of those were, but those rules that you learned were the rules for the transcendental functions. Those are transcendental functions, okay? So some calculus books are actually written in such a way that they're called early transcendentals, and so the transcendentals are done with the polynomials and the other derivative rules that you do. We don't have a book that does that. Our book has the later transcendental functions. So transcendental functions, probably not going to end up writing them all down, but just to give you some examples. Y equals e to the x. That's a transcendental function. Y equals natural log of x. Y equals, I'll just use an a to the x, so some other number that's not e. Those are transcendental functions. And then also, these are not transcendental, but they also sort of come in this category of what we're talking about today, are our trig functions. Now, all of these functions that are on the board are distinctly different than polynomial functions in the fact that with polynomial functions, if you take a derivative, you can only take a derivative so many times before it completely becomes zero. Are you with me? Okay. Transcendental and trig functions don't do that. You can take infinitely many derivatives and they never become zero with transcendental functions and trig functions, right?
Did you say trig functions are transcendental?
They're not transcendental, but they're categorized in this way. So like where I put up here and put transcendental, I could also put and trig. I wasn't thinking about them when I wrote my disclaimer at the top of why we're doing this. Trig functions are as well. Okay? So they have that sort of distinct characteristic difference than polynomial functions. Polynomial functions are really nice. That's why you learn to do derivatives with them first, is because they're very clean to work with, very nice to work with. So what our goal in this section is to take one of these transcendental functions or a variation of it. You know, so maybe it's not e to the x, maybe it's e to the negative x. That's not that's my second example actually. And we're going to create a polynomial function that approximately is the same as the transcendental function, at least in a nearby windowed area. Okay? Because polynomials are so much nicer to work with. That's the why. That makes sense. So we're going to take something that's not a polynomial and we're going to create a polynomial that's approximately the same using series. And we're not going to actually do the whole series bit today. That's going to be in a later lesson. We're going to do Taylor series. We're just doing the polynomials that stop at a specific point today. So let's take a look at a definition of how this is going to work. So if a function f has n derivatives, at some value c, then the polynomial P sub n equals f of 0 plus f prime of 0 times x. Oh, I'm sorry, I'm on the wrong line. It's not zeros, they're supposed to say c's. I was like, that doesn't sound like what I was supposed to be doing. Those zeros are c's. My next one that I'm going to do, it has that in there. So f prime of x, c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus f triple prime of c over 3 factorial times x minus c cubed. And we're going to keep going out until we get to a specific stopping point. It will be given to you in the problem where you're going to stop for your problem. So we're going to call it n. We're going to take the nth derivative at c over n factorial times x minus c to the n. And this massive thing, which is not terribly complicated to calculate, but this massive thing when it looks like this is called the nth Taylor polynomial. And for clarification, it's for our function f at the point c. Okay, I have one more of these like this to write, so I'm going to give myself a little more space. All right, second definition. I feel like it's like second song, same as the first, change a little bit, got a new verse kind of thing. So this is the same. Okay, so if a function, or in the case, we'll say it that way, in the case where c equals 0, we would have P sub n of x equal, or P sub n of 0 rather, the other one was P sub n, it's P sub n of x. It's evaluating at 0. Okay, P sub n of x is equal to f of 0 specifically plus f sub prime of 1 times x plus f double prime of 0. Did I say 1? I didn't mean 1, I meant 0. Lots of zeros, we need zeros. And f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed plus, and again we've got those dot dot dots, f nth prime of 0 over n factorial times x to the n. And this also has a name. This is called the nth Maclaurin polynomial for f.
What is different from the second than the first?
Good question.
Plain as zero.
Okay, we've got zeros plugged in for all of our c's. And lovely things happen, of course, because it simplifies things, right? So I mean, obviously, like the inside function of our zeros. But also notice like this x minus c isn't there, it's just x. So I don't have x to the x minus c cubed, I just have x cubed. It's obviously a very specific case, right? It's kind of like saying polynomials, and then we're saying, well, we're really going to talk about quadratics, right? Quadratics are polynomials too, but there's some really nice features that I can deal with quadratics in certain ways because they're a simplified, specific type of polynomial. So here, a Maclaurin polynomial is a specific type of Taylor polynomial, just the case when x is 0. Okay? Or when c is 0, not x, I'm sorry, c is 0. Okay, so I'm going to show you how this works and the lovely things that we're going to talk about. If you have your calculator with you today, we will also look at a graph here in a little bit to kind of get a sense of what's happening when we're doing this Maclaurin or Taylor process. So we're going to find the Maclaurin polynomial for a couple of examples first. So our first direction set is that we're going to find the nth Maclaurin polynomial for the function. And I'm going to do one trig function, and then I'm going to do one transcendental function. So here's our first one. Our function is going to be cosine of 2x. And we're going to do this for n equal to 4. So we're not going to find the nth Maclaurin polynomial. We're going to find the fourth Maclaurin polynomial. That's what the n equal 4 means. Okay? It tells you how far through this process you have to go. When do I get to stop? I get to stop at n equal 4. Okay, so let's take a look. What I have to do is I have to find all of these, in fact, I'm going to come back over here. I have to find all of these derivative values, right? I need the original function, I need the derivative. Actually, I'll use my Maclaurin one since I'm talking about that one. I have to find the original function at 0, I have to find the derivative at 0, the second derivative at 0, the third derivative at 0, all the way to the, in our case, the fourth derivative at 0. That's what I have to do. So what I'm going to do when I'm processing that is simply to find all those derivatives. So we're going to find, we already found f, or we already have f, so we're going to find f prime. So what's the derivative of cosine of 2x? It's close. It'll be a negative, you bet. Okay, I need 4 derivatives. So what's the second derivative here? It's negative what?
4 cosine 2x.
Negative 4 cosine 2x. Okay, so what is it that's making my coefficients change? Not the signs of them, but the actual numbers. Can you guys remember what that's called? Yeah, it's the chain rule, right? I'm asking because most of you haven't come to see me and taken derivative quizzes yet, so I just want to make sure we're remembering. Okay, good job. Okay, how about a third derivative? What's the derivative of negative 4 cosine 2x? All right, so we're back to a positive 8 sine of 2x. And I need a fourth derivative. The fourth is usually where we start putting the number up there instead of the prime notation. 16 cosine 2x. Okay, is everybody in agreement? All that look okay? Fantastic. All right, and we're supposed to evaluate each of these at 0. So we're going to find f of 0, f prime of 0, all the way down to the fourth derivative. Very good. So, what is the cosine of 2 times 0? Actually, let me just make a comment. The 2 inside doesn't matter, right? Because I'm plugging in 0 for everything, so we can just talk about plugging in 0 to the inside of our function. What is the cosine of 0? It's 1. What is negative 2 times the sine of 0? 0. In fact, all of my sines are going to be 0, so I can jump down and put a 0 down there as well, right? How about negative 4 cosine of 0? Negative 4. And 16 cosine of 0. 16. Perfect. All right, so we've found all the information, and what we need to do is we need to compile it all together like it is at the bottom of the screen. Okay? So you have the benefit right now of having it all on the same page where you can see it, hopefully. I'm going to keep flipping back and forth. So we're going to find our polynomial. It's p sub 4 of x. It says that I'm supposed to have the f of 0 value, which we found was 1. Plus, I need the derivative at 0. I'm sorry, the derivative evaluated at 0, and that one was 0, right? So I'll write it in just for the sake of doing it. You don't have to on your homework, but it's there, right? This would be 0x plus, I need my second derivative, and we found that that was negative 4. And once I get to my second derivative, I'm dividing by factorial, so this is over 2 factorial. And it would be x squared. And then, again, I actually have 0 for my third derivative, so it's 0 over 3 factorial times x cubed plus, and then it's 16 over 4 factorial times x to the 4th. Does that look okay? Everybody good with where all the pieces came from? Okay, so in an effort to clean up, we're going to actually go ahead and write this out the way that maybe you would have done it had you been doing it on your own, and I wasn't telling you otherwise anyway. We're going to write this as the same thing but without the zeros in there. Let me get that written before I talk. Okay, where we're headed eventually is that we're going to find p sub n in general where it continues on. This is a series, right? It's a very short series. It's not an infinite series. It's a series right now that's only got 3 terms. Agreed? And there's some patterns of things going on. Agreed? Okay, you can kind of ignore what I've written up here beforehand, but where I am right now, if you take a look at the denominators, and without even calculating it, what would you expect my next denominator to be? Probably 6 factorial. That's what it looks like, right? My numerator was 4, and then it was 16. What would you expect my next numerator probably to be? 64, right? Times 4. Yeah. What's that? Yeah. And then you would expect the x term to be x to the 6th, right? So there's some patterns going on. The more sequenced terms we see, the more we can recognize the patterns. And we will actually be generalizing those patterns when we get to Taylor series instead of just Taylor polynomials and writing it in a compact way, the way we saw the series notations that we were just looking at in the last 6 sections. Okay, so that's where we're headed. But for today, here's where we're stopping. All right, so we're going to do another one of them. I'm going to let you guys have a chance to do this one out by hand, and then we'll compare. So same directions. I'm not going to write them again because you already have them written down. Problem number 2, this is going to be f of x equals e to the negative x, and we're going to do this for n equal 5. So we're going to find the 5th Maclaurin polynomial. Yes?
I have a question about the last one.
Okay, I'm sorry, yes?
Couldn't we simplify that further?
That's a good question. The answer, of course, Becca, is yes, we could. The problem is that when we get to the point later of trying to generalize it, it's easier to see the patterns if they're not simplified.
Okay, so generally speaking, we should leave it.
We're going to leave it. Yeah, that's a really good question. I meant to say it and I didn't. So yeah, we're going to leave it even though, yeah, could I simplify the 4 and the 2 factorial? Of course I could. Could I simplify the 16 and the 4 factorial? Of course I could. We're not going to because of where we're trying to head with the information we're going with. Okay? Yeah. Okay, so let's take a look at this one. You need to find how many derivatives this time? 5. And we're still evaluating them at 0 because we're still finding Maclaurins. Okay, so find me 5 derivatives, evaluate all 5 of them at 0, and see if you can piece them together into that 5th Maclaurin polynomial. Okay, is that what you got so far? Lots of ones and negative ones and derivatives that just keep flip-flopping all the way and they never end, of course. And if you created your polynomial for it, hopefully it looked something like this. Okay, is that what it looked like? Yeah, see all kinds of patterns there, right? In particular, what kind of series is this? It's an alternating series, yes it is. And if we were to start writing out how to consolidate this, if it went on infinitely, right? We would have that -1 to the n, or maybe to n plus 1, depending on how we started it, right?
Big X, the X would be it to the n minus 1.
It depends on what you let your n start at. Yeah, so it would be, you'd have an x to the n or x to the n minus 1. And you have factorials that are increasing, right? Like an n factorial kind of thing in the denominator. So we've got some sort of sense of where this is heading. It's going to be looking something like that when we're done. All right, let's take a look at what happens when we find a Taylor polynomial instead of a Maclaurin polynomial. It's very similar, but it just looks a little bit different at the end. So we're going to do same kind of directions. Find the nth Taylor polynomial now. Centered at C. And the function that we're going to look at is going to be a different one. We haven't done this one yet. 1 over x squared. It's not a polynomial, right? It's not exactly transcendental or trig either.
Do we have what C is, or do we just input C?
Oh, I haven't written it yet. I'm sorry. You're right. A couple things. We're going to do n equal 4, and we're going to do c equal to 2. Yeah. Thanks, Ethan. Okay, so of course it might be useful to remember how to rewrite this, though, like it were, or as if it were a polynomial, or at least an exponential notation. How else could I write 1 over x squared? Yeah, x to the negative 2 would be more friendly, so let's write that down. Okay, so we're going to do a bunch of derivatives, 4 to be precise. So what's the first derivative? Negative 2x to the negative 3. Second derivative. 6x to the negative 4th. Third derivative. Negative 24x to the negative 5th. And a fourth derivative. I'll help you. That's 120. Negative 24 times negative 5 is 120. X to the negative 6th. And we're evaluating these at what value? 2 this time, right? Because it's a Taylor series evaluated at 2. The first one's not too bad. So if I plugged in the number 2 here, what would I get? Right, which would be 1/4, right? 2 to the negative 2 would be 1 over 4. And to save us a little bit of time, let me just let you know, if you were to plug these in your calculator and then turn them back into fractions, basically what these give you, okay? So the second one is actually negative 1/4. The second derivative is 3 over 8. The third derivative is negative 3/4. And the fourth derivative is 15 over 8. Okay, so this is also alternating, right? It is. All right, let's go ahead and put our polynomial together. Piece of 4 of x is equal to 1/4 minus 1/4 times x minus 2. Remember, I've got the polynomial x minus the constant value c. And then I have plus, and it's 3/8 and then the 2 factorial in the denominator, so it's 8 times 2 factorial. And then I have x minus 2 squared minus 3/4, and then again 2 factorial in the bottom. I'm sorry, 3 factorial. I didn't write that one right at all. Is that better? 3 factorial? Yeah. X minus 2 cubed plus 15/8, so 15 over 8 times 4 factorial, x minus 2 to the 4th. All right, so far so good? I mentioned we were going to take a look at your calculator, and I would like to do that so you can see how this is actually doing it visually anyway. So grab your calculator. I would like for you to put into your calculator, to start with, the function cosine of x. So just put in, y equals cosine of x, and then we're going to write a little bit down about this so you can see what would be happening. So we can approximate actually, we're going to do the one we started with. Actually, that's what I decided to do. We already found them already, so it makes it easier. We're going to do this one, the cosine of 2x, number 1. Cosine of 2x. That's what's going to be in your calculator. Okay, so we can approximate the value of a transcendental function. By using the Maclaurin or Taylor, just depending on which one's appropriate, polynomial. And we're going to consider example 1. Okay, and on example number 1, we had f of x equals cosine of 2x. And we had a polynomial, piece of 4, I think is what we found, wasn't it? We had found piece of 4 and of x. And it equaled 1 minus 4 over 2 factorial x squared plus 16 over 4 factorial x to the 4th. And we even sort of talked about what would happen if we went out 2 more terms. The 5th derivative would have been 0, and then the 6th derivative would add 1 additional term. So just for the sake of looking at patterns here, I've got everything I already have on the screen before. And what would happen next? Would I have a positive or a negative? It's negative. They're alternating. I'd have 64 on top over 6 factorial on bottom, x to the 6th. Okay, so this is what it would look like if I had the 6th polynomial. So what I'd like for you to consider is, let's take this one, the piece of 4, and I'd like for you to put it into y2 in your calculator. Okay, so ignore the piece of 6 for the moment. Let's just make this y2, and your original function that I already had you put in was y1. Whoops. And I can't keep recording if I switch to a calculator that shows me a graph at this point, so I'm just going to sketch approximately what I'm getting on mine, okay? Okay, so you know that the cosine graph just oscillates down and up between -1 and 1. It hits the x-axis right here at x equal or y equal 1, and it comes down and it goes back up. It's an even function, if you remember that. It's got this nice cyclic pattern to it. It's not supposed to go up that high because it's supposed to not go above 1. So at least make it look legit. There we go, and it's going to go back down. Okay, so it looks something like that. So my red graph here is going to be my cosine graph. So y equals cosine of 2x. Okay? Now when you drew your first graph, when I asked you to put in P4, if you look at a window, I'm going to say maybe about -pi to pi should be about sufficient. So make your window, if you have your calculator and you haven't done it yet, hit window, make x minimum -pi, x maximum pi. Okay? And you're going to get this picture. This is exactly what cosine looks like between those two. All right? And then what's going to happen is that your polynomial looks something like this. Excuse the not so prettiness of it, but it looks like a W, kind of. And what we're doing, or what we should be noticing, is because this is the Maclaurin series, right? So it's centered at 0, is that if we look in this area, the graph, if you were to zoom in at that vertex, not vertex, but that maximum point, that relative maximum on the graph, they're almost the same. They're very, very, very close to the same y values in that small area nearby, right? So just for fun now, turn y2 off or erase it or add to it if you want. I want you to put in p sub 6 and see what changes when I use p sub 6. So I still have the same cosine graph. But then the graph does something like this. It's got some weird squigglies down at the bottom, but it ends up opening downward overall. And I actually get an even better approximation through here than I had before. It gets even closer. So what do you think is going to happen if I found P8? It's going to get closer, and then it's going to get closer to hitting those loops on the end, right? So the further we go along with this, the more of the curvature we're going to get further away from 0. Does that make sense? And if you did it forever to infinity, you'd essentially be the same thing. You would have a polynomial that is the equivalent of the cosine of x. It's crazy stuff. Now, just for kicks and giggles, we're going to do one more thing here, which is very interesting. You'll have a couple examples of this in your homework as well. I would like for you, keep your graph going. I mean, not your graph, but keep it in your calculator. We're going to approximate the function using the polynomial found. The directions will say found in previous problems when you get to this in your homework, and it'll tell you which problem to look back at. So if it says look back at problem 13, I know I was careful to assign problem 13 as well. So you're going to have the expansion already. I'm not asking you to recreate anything. I'm just asking you to refer to what you did before. So that the polynomial found, we'll say earlier for the purposes right now. So what we're going to look at is we're going to look at finding, and we're going to use, oh, I didn't do it for this one, but that's okay. We'll do it for this one just for fun. Let's say what happens when we would find f of, oh, let me write it down. We'll use the same f of x we just did. This isn't in my notes now, so let's hope it works out. Cosine of 2x, that's my function that we just talked about and looked at a graph for. And we know that this Maclaurin series that we just did is centered, of course, at 0. So the closer I get to 0, the better the approximation should be. So we're going to choose something, or we're going to approximate something that's roughly speaking near 0. So let's actually find this at x equal 1/4. Okay? So how are we going to do that? Well, I would like for you to find out, just for the sake of seeing how close it is, let's find p sub 4 of 1/4. And again, if your calculator is set up to do that, you should be able to just put that into the table. You don't have to enter it by hand. Just go to your table and do it. And then we're going to find p sub 6 of 1/4. And then we're going to compare them, because we have a calculator to do that, to actually finding the function value cosine itself at 1/4. And since I didn't do that one in my notes, I'm going to do that one with you. Okay, for my first polynomial function value, P4, I got my 877, I don't know how many decimals I need. I'm going to go with maybe 6 of them for now. 877604.
Oh.
Is that what you guys got? Okay.
No, I did 1/4 for C.
Oh, no, not for C.
Yeah.
1/4 for the F value that we already had. In the second polynomial, I got 877626. And if I plugged it in, and these are all approximates, this is terrible notation, approximate, because of course they're not terminating decimals. And then the function value itself, when I plugged it into cosine, I have is 0.87758. So look how close the numbers are. Did I get them? Is that what yours are? Mine screwed up.
On P6, did you add association?
I did. That's exactly what's wrong.
Okay.
Okay, let me fix it. Hang on. It was like it should be closer, but it isn't. Okay, good deal. You guys caught my mistakes. No worries. I was just testing you. And it worked. So good. Okay, I have 877582. Excellent. Okay, so even just at P4, the approximation is pretty good. I mean, you're correct to the thousandth place, right? And I don't know, you probably send significant digits to me and things like that, and I don't care. But it's 3 digits accurate, right? 3 digits and we're good. Once we got to the 6th one, we're actually good to 5 digits. It's pretty impressive. So this is, and that's not going out very far. This is not very many, we're talking about doing something eventually here where it's an infinite process, right? This isn't an infinite process. This is a very finite number of terms that we've considered, and we're already getting an extreme level of accuracy in our values. Okay? So cool stuff. Let me give you some homework, because no weekend would be complete without it. I know. Okay, so this is page 644. Numbers 13, 16, 20 and 21. 25, 28, 29, 41, 42, and 43. And web assignments out there as well. What do we do on Monday? Happy weekend.